Hello. Today I will present a study on direct policy search as an alternative to POMDP for sequential decision problems in infrastructure planning. My name is Bismut and I am a PhD student at the Technical University of Munich. Population growth, increasing traffic loads, or climate change are all variables that threaten to make our current infrastructure obsolete and unable to keep up with the changes. As infrastructure upgrade is costly, good planning is needed not only to determine the initial design, but also to include the future event into our planning policies. However, policy optimization for reef structures is a very complex sequential decision problem. This presentation will tackle two questions. The first one, can we identify a simple heuristics to approximate an optimal strategy for infrastructure planning throughout its service life? And how good is this approximation? Let's take the example of a generic planning problem. For instance, a water treatment plant in a city. Many questions arise. What is the future demand? Is it worth building with a great capacity surplus? Or could the money be invested in a later upgrade? These questions are quite difficult to answer because, for instance, the demand on a population increase is a random process and it is associated with a high uncertainty. This influence diagram represents this random process, where the round nodes are random variable and the square nodes are decision nodes, such as increasing a system capacity. The diamond node, on the other hand, are costs. In this study, we consider two types of costs. The first one is a penalty for the demand exceeding the capacity, and the second one is the cost that is incurred when we want to upgrade the capacity by a certain amount of units. Here we consider a fully flexible system, which means that the upgrade cost will vary linearly with the amount of capacity that we want to add to our system. In our problem, we have the opportunity to take an action at every time step. This action will eventually impact the lifetime reward cost, whether it's increasing the capacity or just leaving it as it is. Obviously, the number of possible decision paths is huge. However, we can structure our decisions by following a set of policies. A policy is a function that assigns an action based on our knowledge of the system. The strategy will be the set of policies for all the years, and obviously the chosen strategy will impact the lifetime reward cost. The aim of our problem, finally, is to find an optimal strategy which will minimize the expected total lifecycle cost, as shown by this equation. As we've intuited previously, the sequential decision problem in general is an intractable problem because the complexity increases exponentially with time and with the number of states that the system can take. There have been several attempts to solve this problem, notably in the framework of POMDP, or partially observable Markov decision processes. The approach proposed by the POMDP framework is to replace the random variables, the annual demand and observation outcome, by a single variable, which is the belief state. The belief state obviously is a multidimensional variable, and it represents the probability distribution of the state of the system. So in this case, the POMDP is transformed to an MDP, or a fully observable MDP, on the belief state. However, the solution is still not tractable in the general case. But in the particular case of a Gaussian POMDP, where all the variables and the transition probabilities are Gaussian, the belief state is actually summarized by a few parameters, which in this case consist of the mean and standard deviation of the demand. The problem then becomes tractable, the solution is exact and gives the optimal policy at every time step. The shape of the solution then takes this form. The solution then is basically a matrix where we can read in the x-axis and the y-axis the values of the belief state, and in a color the associated action at that particular time step. I will not go into details as to how the POMDP is solved, but I recommend a few references to read on the subject. But what if we had another solution in order to find the exact optimal strategy for a problem? So we propose a direct policy search with a heuristic approach. Basically, we define a set of few parameters, and with these parameters we describe strategies that belong to the space of all possible strategies, and we perform the optimization within this reduced space. Obviously, the selection of the parameters will determine how good this approximation is, and the aim is to find a heuristic which will find a strategy that is as close as possible to the true optimal solution of the sequential decision problem. So let's choose some heuristics. We investigated 3. All 3 have to choose an initial capacity of the system A0. But the first heuristic will upgrade the capacity at fixed time intervals delta t by a fixed amount delta A. Heuristic 2 will behave quite differently. It will upgrade the capacity by a fixed amount delta A when the probability that the demand in the next year exceeds the capacity is higher than a threshold PTH. For heuristic 3, it will upgrade the capacity by a fixed amount delta A when the measured demand is within K% of the capacity, acting as a safety margin. The optimization then acts over these few heuristic parameters instead of the full spectrum of the strategies. We used a cross-tree method as a noisy optimization method to solve this problem, but there exist several other methods that solve such noisy optimization problems. In this case, the objective functions of this optimization function is the expected cost of the heuristic strategy. We can calculate it actually with a Monte Carlo simulation of the demand and then the observation. And then we can actually simulate how the strategy would prescribe the capacity to be upgraded during the lifetime of the structure. Then for every simulation, we can calculate a lifetime cost. And on calculating the average over all these costs, we can get not only the total expected cost, but also the annual expected cost. One of the advantages of the noisy optimization method is that this simulation and this estimation of the cost for a strategy does not necessarily need to be extremely accurate. So it does not require a high amount of samples for the Monte Carlo simulation. In the extreme case, we could also only use one sample per strategy evaluated. This will affect how fast the optimization method will converge, but it has shown that we obtain quite stable results by choosing even one sample per simulation. Now on to the results. What we found is that for heuristic 1, the initial capacity is to be of 3 units, and the interval at which the system needs to be upgraded is 65 years for a structure that lives 400 years. This means only upgrading the system once. For heuristic 2, the initial capacity was prescribed as 2 units, and the probability threshold of 1.16 10 to the power minus 5. For heuristic 3, the initial capacity is also 2, and the margin k equal to 0.12. For all 3 heuristics, the fixed upgrade delta A was equal to 1. In this graph, we can see how the 3 strategies and the strategy prescribed by the POMDP behave in presence of a scenario of demand and observation. We see notably that heuristic 1 is not very flexible. Indeed, it only upgrades once at 65 years and cannot react to any information about the demand itself. On the contrary, heuristic 2, 3, and the strategy given by the POMDP react quite flexibly to the information, and actually heuristic 2 and 3 are very close to how the POMDP behaves in that particular scenario. We can also have a look at the mean capacity prescribed by the 4 strategies. And here again, we see that heuristic 1 actually has only one choice, which is to upgrade from 3 to 4 at year 65. And heuristic 2 and 3 follow quite closely the solution prescribed by the POMDP, at least in terms of expected prescribed capacity. But now let's look at what actually we are interested in, which are the expected total costs. As we could have predicted, heuristic 1 doesn't perform very well, not so much in terms of cost of upgrading, but in terms of expected penalty. It is not flexible enough to be able to react to how the demand varies. On the contrary, heuristic 2, 3, and the POMDP solution almost have the same expected cost, with heuristic 2 being the closest to the POMDP solutions. Hence, heuristic 2 would be the best heuristic in this case to compete with the POMDP solution. Heuristic 3 is also very good, but we should remember that it is based on the measurement itself of the demand and not, as heuristic 2, a probability of exceedance. And the performance of heuristic 3 will of course be very dependent on how accurate this measurement is. And we would expect that for a higher measurement error, heuristic 3 would not perform as well as heuristic 2 or the POMDP solution in that case. Since we have attributed the victory of our competition to heuristic 2, does that mean that they actually behave the same when we are looking at the yearly policies? In fact, they don't. Here we see in the 4 graphs 4 different policy matrices for, on the top, the POMDP exact solution, and on the bottom, the solution proposed by heuristic 2. We can see that they're quite different. Although they are both stationary, heuristic 2 does not present the same features as the POMDP solution. In particular, heuristic 2 is not able to represent how the POMDP indicates that at the end of the lifetime, it is not necessary to upgrade the system anymore if the observed mean of the demand is too high, as is shown by this very thin but present dark blue line for the state mu t equals 6 and the capacity of 0. Obviously, it's not a very realistic situation to be at t equal 99 and not have any capacity built in, but still it is a feature that the heuristic 2 cannot represent. In conclusion, we've shown that the direct policy search with the choice of heuristics for infrastructure planning can yield a quasi-optimal solution to our sequential decision problem. One of the advantages of choosing a heuristic approach is that we can adapt to the constraints of the operator and define heuristic parameters that will satisfy its needs, for instance, a regular upgrading interval or a constant capacity upgrade. In fact, heuristic strategies have the advantage of being more transparent than the strategies within the framework of POMDP. POMDP will give a sort of user manual, but it will be very difficult to predict in which direction it will lead us. Whether the heuristic strategies, we will know in advance what kind of features it will present during the lifetime. Furthermore, the heuristic approach is not limited to Gaussian distributions, and the noisy optimization methods are particularly straightforward to apply within the DPS approach. The study also revealed the sensitivity of a problem to the assumed cost functions and the measurement accuracy. These are a few of the references that have been very useful to put together this study. And with this, I would like to thank you for your attention, and I look forward to seeing you all in Seoul.